All right, guys, this is our second video for 6.2. And in this video, we are going to talk about how the dot product can help us find the angle between two vectors when those two vectors are arranged tail to tail. So right here, we've got two vectors with standard representation, u and v, on the xy axis. And right here, we can see the angle between u and v as this angle right here, theta. Now, right here, if I drop a perpendicular from u onto v, I have a sort of tilted reference triangle, right, where u is the hypotenuse, and the projection of u onto v is the adjacent, right? So right here, because we know that cosine is going to relate the lengths of the adjacent and the hypotenuse, we can say cosine of our angle theta is going to be the magnitude of the projection of u onto v over the magnitude of v. We've got that ratio right there, right? Now, we have a definition of the projection of u onto v, so we can substitute that into the numerator, right? And using that definition, we can say that right here we are going to have the magnitude of the scalar u dot v over the magnitude of v squared times the vector v as the projection of u onto v. Now right here, we know that the magnitude of a scaled vector is equal to the magnitude of the vector times the scalar. So right here, what we can do is take this scalar and essentially say that we can evaluate the magnitude of the projection of u onto v as the scalar of u dot v over the magnitude of v squared times the magnitude of v, and that's over the magnitude of u. Now at this point right here, we're going to take this little formula and bring it down, and we're going to say that we can first cancel one of the two magnitudes of v we've got in the denominator of our scalar with the magnitude of v we've got there, and then when we multiply by the reciprocal of the magnitude of u, we've got cosine of theta. I'm going to have to sort of find some space for this. I think we've got it as right here u dot v over the magnitude of u times the magnitude of v. Now right here, when we apply inverse cosine to both sides, what we're going to get here is theta as the inverse cosine of u dot v over the magnitude of u times the magnitude of v. And right here, that's the formula we're going to use to evaluate the angle between two vectors connected at the tail, right? So right here, what I want you guys to do is to go ahead and use this formula right here to evaluate our angle theta, where we've got our vectors u and v defined right here, just like they were on the last page. We're going to pause the video now and let you guys go ahead and use that formula to evaluate the angle theta between u and v. All right, so plugging all this into inverse cosine, we've got the dot product of our vector u, 3, 5, and our vector v, 8, 2, over the magnitude of u times the magnitude of v, right? So we can simplify this a little bit. Dot product is pretty easy to find. These guys look intimidating, but really we can say that's the square root of 34 times the square root of 68. And then right here, when we multiply 34 and 68 under one square root and evaluate our dot product, we've got 34 over the square root of 2,312. And when we type all this into inverse cosine, we get 45 degrees. So this is a little bit crazy, but one of the things we can sort of spot here is if we take what's inside that inverse cosine and say we've got 34 over the square root of 34 times the square root of 68, really when we multiply all of this business under one square root, we can say that we've got 68 as 2 times 34 times 34, right? So that right there is going to give us 34 over the square root of 2 times 34 squared, which is, of course, 34 over 34 square root of 2. And right there, when those 34s cancel, we have 1 over the square root of 2. And if we were to rationalize the denominator, multiplying by the square root of 2 over the square root of 2, we get the square root of the square root of 2 over 2, which is obviously a stop on the unit circle. And so right here, it makes sense that we would evaluate that guy and get 45 degrees. Okay, so right here we want to talk about some different types of vectors related by right angles and basically angles of 0 or 180 degrees. So right here, orthogonal vectors are two vectors that are perpendicular. And with orthogonal vectors, what we can say is that when we take the dot product of two orthogonal vectors, we're always going to get 0. So right here, we've got u and v, which we can visually tell are two perpendicular vectors. And right here, we've got their component forms. And if we take the dot product of u and v, we would then get right here the product of the horizontal components, so that's -2 times 3, plus the product of the vertical components, so that's 6 times 1, which is going to give us -6 plus 6, which gives us 0. Now right here, one of the things that we can think is that we know that the dot product of our two vectors u and v is actually equal to the magnitude of the projection of u onto v times the magnitude of v, right? So if we look at this, we know the projection of u onto v, right, is the component of u, or the amount of u that is going in the v direction. And if we're perpendicular, we can say that actually none of u is going in the v direction. So really what we have is 0 times the magnitude of v, or 0. And that's sort of one rationale for why we get 0 with the dot product for perpendicular vectors. Parallel vectors, we say, share the same direction and differ by a scalar. So right here we can say two vectors are going in the same direction, or opposite directions, we might say, if the vector was if the arrow was going in the opposite direction here. If they have if they differ by a scalar. So right here we have w and v as two vectors that appear to be parallel. And right here, if we were to take a look at v, let's just sort of write component form of v. We've got 3, 1. And we can see that our vector w, 6, 2, is really 3, 1 times the scalar of 2. So in that way, we can say that basically we've got two vectors that are parallel or headed in the same direction. And we say in general that the 0 vector is orthogonal to all vectors. Okay, so that's this video. We've got one more video to look at where we're going to start taking a look at vectors in the real world. So stay tuned for that. One more video.